Now, it's my honor to introduce our keynote speaker, Professor Douglas Jones. He is now a professor at UIUC, a director of ADHD in Illinois. And he's also an IEEE fellow, the author of 2 DSP textbooks, and also the board of governors of IEEE Signal Processing Society from 2002 to 2004, among others. He will give us a keynote speak on biologically inspired audio today. Now please join me to welcome Professor Jones.
Well, thank you very much. Let me get you hooked up here real quick. Is that coming through? Oh, really? Is that all right? Okay. Okay, well, thank you very much for the welcome and for the opportunity to speak with you here today. So it's, for me, I got involved in biologically-inspired audio processing about 17 years ago when a colleague from neurophysiology asked me to participate in a hearing aid project. And so I thought it might just be of interest to you for me to kind of share my experiences in working with biologists and trying to build our audio, mostly our audio, but also some multimedia algorithms based on some biological inspirations. And just kind of tell you kind of how it's helped me anyway, and then maybe some ideas for how we can get insight from biology to help us solve some of the challenging problems that we face in multimedia. So, I mean, before my colleague got me involved in this project, I really wasn't very interested in biological inspiration. I mean, he was interested in working with the binaural hearing aids. So, hearing aid that had 2 microphones in each ear and would basically beamform, combine the signals from the 2 microphones to process. And I'm thinking, well, this is a solved problem, right? I mean, we've been doing audio and acoustic ray processing for decades. You know, there's sonar out there. You know, we have mobile phones, the audio we have home, we have Skype, we have all the systems, and so most of the algorithms that we use are more than 30 years old. So I think as an engineer, this is a very mature field. I mean, surely there can be some more research to do. And so I was pretty much content to think there wasn't really a lot to be had until my colleagues started educating me about some amazing animals. And so it turns out that the auditory systems of many animals are much superior to the systems that we as engineers can build today. And so we don't really notice because we have our binaural processing system, and we're really amazing. Since we're so natural to us, we don't even realize how good we are. So we can actually, and the psychologists have studied this carefully, can be in an environment you have maybe up to 6 people surrounding you, all talking at the same time, simultaneously, and we can actually listen into any one of those 6 people we want to. We can hear their speech and separate it from the speech of the other people, and we can find their location with our eyes closed within about 2 to 3 degree accuracy. And we can do this only 2 years, so essentially we can solve the cocktail party problem. But it turns out that our best signal processing algorithms from kind of the engineering side they can't really deal with this. They can only deal with 2 sources at the same time. And so this is kind of things like, well, how do we do that? It's just kind of amazing. And so this is something that our biology can do that our signal, that is, in spite of the decades of signal processing research, we haven't figured out how to do. And there's another animal which I'll tell you about in a little bit, which is called this fly. And so another issue is that there's this fly that has an ear which is less than 2 millimeters across, like an ear that large, and it can determine the direction of sound within 2 degrees. How does it do that? Right? It's just amazing. So there's animals have some capabilities that we just don't have. It would be very useful for certain types of multimedia systems. And so this really got me interested. I'm like, okay, well, look, we need to figure out how to do this. So I'm kind of a strong AI guy. I believe that if animals can do it, we can do it too. Just we need to figure out what the trick is. And so again, this got me very intrigued. And because I couldn't figure out how to do it on my own, I thought, well, I'm going to work with the biologists to see if they can help me understand what the tricks are so that we can actually figure out how the animals do this. Because I wasn't getting anywhere by just thinking about it as an engineer. So again, our goal has always been with this work has been to try to come up with similar capabilities and performance to these animal systems that I mentioned. But because I can't figure it out on my own, to see if we can figure out how some tricks from biology to see if we can turn them back into techniques and algorithms that will be able to do that in engineered systems. And so again, but before really important to understand exactly what it is animals do that's so amazing, So again, one of the critical things they can do is they can separate and locate sources with high accuracy and with many more sources and sensors, so it's going to be under the source separation problem, with only smaller microphones, so say 2 to 4 microphones. And that's important because if we want to put these microphone arrays on things like cell phones and mobile devices, or maybe even like pens and stuff, very small devices, then we need to be able to figure out how to compress these things down to very small arrays, small number of microphones, small aperture size, and to make that work. So that's one driver for me, was to try to understand how we can build small arrays we can put on very small portable devices. And I've also been very interested in being able to do 3D recording with very small devices as well. I mean, I like 3D audio a lot, so I've really been interested in, can we put a 3D audio where I can say with a cell phone, and can I record a video with a camcorder on my cell phone, and then get that full audio experience of being there in the space. That's another area that we've been working on. And another thing that's particularly important, I guess frustrating to me as a signal processor, is that very often when I build algorithms, I do it by running a MATLAB simulation. Oh, it works great. I get 15 dB SNR gain. It's wonderful. I put an anechoic chamber and it does get 12, 13 dB. Great. I go out and use it in a real room like this. 0. It breaks down completely. So our algorithms turn out often to be not very robust to real-world effects, like the echo reverberation in rooms, kind of normal, real environmental noise as opposed to like Gaussian noise that I simulate in MATLAB. And so, but animals are amazingly robust. They can be in very complex environments and still perform just about as well as they do in the ideal conditions, sometimes even better. And so the question is, how do we build algorithms that are inherently robust to the environments as opposed to very sensitive and fragile? So that's been another reason that I've turned to biological integration. And finally, I've also been more recently interested in energy efficient systems. If we want to have small mobile devices we can run for hours to do interesting audio processing, well, we need to figure out how to get the energy cost of that down to the point where we can use small batteries. So that's another place where I've turned to biology for some inspiration as well. So I'll just kind of take you on a tour of the various ideas that we've borrowed from biology and how that's turned out for us, and addressing some of these issues here. And again, I'm just hoping that maybe the experience will be at least of interest to you and perhaps inspiring and helpful. So let me first start with the first problem I worked on, which is audio source separation. And here the biological inspiration was a human auditory system, or human hearing. So as I mentioned, I first got involved in this, involved in the hearing aid project. And so it turns out if we use our standard algorithms, if we have 2 microphones, say in case of 2 ears, then we should be able to separate 2 sources. So 1 target, 1 interferer, and if you add more sources, we shouldn't be able to do it. And so I was perfectly happy with that result, because that's what the signal processing theory says, until my colleagues pointed out to me that, hey, humans do just fine. You can have 3 people, 4 people, 5 people sit around the table, go to a noisy restaurant, and you can still hear the person you want to hear quite well. So somehow we don't have that loss and degradation when we get to the more sources and sensors. And somehow we do it with 2 ears. They've discovered if we plug up 1 ear, we definitely lose the ability. So it's something about 2 ears. There's some kind of beamforming or array processing going on. But the question is, what's the secret? How do we do that? So that again really intrigued me. It was because I didn't have any ideas myself on how to solve that problem. We turned to biology. Now, how do engineers solve that? Let's sort of talk about how the standard engineering approach. Engineers use what's called the Griffiths-Gem beamformer, the generalized sidelobe canceller, and this is really the state of the art of what we typically deploy. And it's called an MVDR, minimum variance distortionless response beamformer. And essentially what it means is it has what's called a distortionless response constraint. It says recover the target with no distortion, so capture the signal without any change. But then minimum variance says cancel out as much of the other energy as possible, so reduce everything else, maximize the SNR subject to distortionless response. That's really kind of a clever idea. If we have 2 microphones and we're listening to the source, say, in hearing aid, I want to have 2 microphones here, and I want to hear the source straight ahead. Well, the signal that I want to keep should be the same on both ears. In that case, I have the signal, the good stuff is the same on both microphones, and the noise that's coming from different directions should be different because it has a different time delay and some head shadowing and stuff. So the basic idea is behind the generalized sidelobe canceller is, first of all, add the signals together. And of course, that should give us constructive interference of the target. It should be twice as large, so it's a good thing. And then we subtract the signals in another branch. And the trick behind subtracting the signals is that then that should cancel out the signal in this other branch. So we should be left with only a mixture of the noise components in this branch. And then I can run an adaptive echo noise canceller. So since I borrowed from the adaptive noise canceller literature. Essentially, I take this output, I run it through some kind of adaptive filter that tries to manipulate or modify this signal to make it look more like the sum of the noises. And if I'm lucky and it all works out right, then it'll cancel that out, and then leave just the target behind. So that's the basic idea behind the GFC. And again, it's the state of the art, it's what we typically always use. And again, that's kind of the classic algorithm which was developed in 1982 and is still generally not really surpassed in the literature. So how does it do? So what I want to do is show you a plot here. So this is a performance with the signal noise with 11 what I call configurations here. So to explain this, again, I was interested in hearing aid problems at first. So in this case, our configurations are all the source I want to listen to is straight ahead. So I'm looking at the person I want to hear, and then I have an interfere, either 1, 2, 3, or 4 interferes at different locations in space. So for example, configuration 1 is I'm target straight ahead, the interfere is at 30 degrees off to the left. Configuration 2 is the interfere is at 45 degrees off to the right, and so forth. So anyway, the question is, so how well does the generalized side-lobe canceller do in canceling out the interference and getting us over this interfering noise? Well, it does it great. If you have one interfere, it can get up to about 10 dBs in our game, which is really pretty good. But then if you have, say, 2 or more, well, suddenly the performance drops down to about 3 or 4 dB. So again, it suddenly just drops off, really, and you get relatively a little bit of gain, but really not very much at all. So not enough to really be particularly useful. So again, that's very frustrating. But then again, but first, before 1997, when I first started collaborating with my biologist friends, I was like, well, this is exactly what I would expect, right? The mathematical theory says, 2 degrees of freedom. I can use 1 to target the signal, 1 to cancel interference, 2 microphones, 2 degrees of freedom. That's all I can do. So of course, this is exactly what we'd expect to happen. I shouldn't expect anything. And again, it wasn't until we asked, but wait a minute. But I can go to a noisy restaurant or a party, and I can deal with 4 or 5 interferes. So obviously, there's more to the story. But my normal kind of white Gaussian noise, mathematical theory doesn't tell me exactly what the story is. So that's the question that really intrigued us when we first started on this project. So the question is, well, okay, how does our brain do it? So we certainly don't know everything. The biologists don't know everything about how the system works, but they know some things, enough to give us some hints. And so it turns out, again, we're really good at the cocktail party problem. And it turns out that the way the brain works, again, we know something about it, not everything. And so essentially there's separate neural circuits in the brain. It's actually kind of weird to an engineer. There's 2 separate circuits in the brain, one of which processes relative time delays between sound arriving at the 2 ears, and another one which processes different the intensity, so the relative strengths of the signals on the 2 different ears. And somehow it splits the signal into different frequencies, using so the cochlea in our ears separates the sound into different frequency bands. Each band, the brain separately processes the sound at the different time delays and different intensities, and somehow uses that information to select a source of interest and to cancel out the other sources. And so it turns out it's also known now by the biologists and psychologists that mostly at low frequencies below about 1 kilohertz, we do that almost entirely using time delay, kind of ignoring intensity differences. But above about 2 kilohertz, our brain pretty much ignores the time delays and only uses the intensity differences. So somehow this is kind of how the brain does things. Well, so they know a bit more about kind of what the processing is, how this is done. And actually back in the 1950s, a lot of electrophysiologists sticking needles in brains have discovered there are actually circuits in the brain that do some of this processing. And they even know exactly where they are in the brain, in cat brains in these studies. So basically the idea is that there's something called the dual delay line model, which Jeff has introduced and showed actually by sticking needles in brains and finding specific neurons that actually respond to exactly these kind of stimulations. So fast signals coming into 2 ears, the model is that essentially the sound comes in and kind of goes down a delay line where essentially it gets delayed by different amounts here, and essentially the brain just kind of cross-correlates the signal at each frequency band with different delays. So essentially what it's doing is looking for a time delay, which of course corresponds to a specific direction that maximizes the correlation between the left ear and the right ear. So simply looking for coincidence between the sound of the left ear and the right ear, and then somehow mapping that relative coincidence back to a direction. And what it does with that is less well understood, but it's known that the brain has actual neural circuits in the brain that do precisely that. So my colleagues introduced an algorithm to do the same kind of thing. Here's kind of a map of their output of their technique. And so since if we have sources that are located, in this case here, I have a source here at minus 60 degrees, then if we sort of look at where should those signs line up, at what delay should we corresponding to some angle, should we see a coincidence, or basically a big alignment of the signals from the both ears, which should be identical? Well, that will happen essentially, of course, at that angle of all frequencies. And then actually at higher frequencies, we get kind of a pattern here. Because at higher frequencies, there's a 360-degree phase shift at different angles. And so we kind of get these ambiguity lines where we can see that, there's, we align it with one cycle off, then you can also get these coincidences. So we see these patterns kind of like this. So to build an algorithm that essentially does precisely that, it separates the sound into 1,000 different frequency bands, does essentially cross correlations between them, looks for the peak alignment where the cross correlation is highest, and marks that. And if you build an algorithm that actually does that, and so here's kind of the output of the algorithm at a particular time. So in this case, they have interferes at 60 degrees, target at 0, and another interfere at 45 degrees. And what you can see as you look in this time frequency pattern, this coincidence pattern, you'll see that in this case, at this particular time, we see a pattern associated with the source at 0 degrees. So essentially, these are the peaks of the coincidence. And so you can see that in this frequency range, there's a source dominating at 0 degrees. You can see at the higher frequency range, there's actually a source which is at 45 degrees. You can kind of see a dominant pattern. And at low frequencies, you're starting to see kind of a mess where they're all done. At some later time here, then we actually can see that there's a kind of an interference and a mixture of sources at 60 to minus 60 degrees and a source at 45 degrees. You can see these characteristic patterns. So you can actually use that then to go in and look in this type of display, which again is mimicking the neural processing. And you can actually successfully separate and identify the locations of sources and use that to help guide your separation. And so that's one way you can do it. The only problem with this is back in 1997 when they first introduced this, in a manner that took 12 and a half hours to process 1 second of speech. So really interesting algorithm, but it turns out that the implementation of that, which is kind of a straight copying of the biology, was too slow to be practical, particularly for hearing aids, which only have a 5 megahertz clock rate on them. So what we did is we actually kind of stepped back a little bit. We said, okay, well, let's not worry just about how the ear does it. Well, let's see if we can understand why the ear is doing it, what the trick is, and maybe we can figure out a different algorithm that achieves the same thing. So after months of interaction between the signal processors and the biologists, we eventually came up to kind of a conclusion as to how the brain, what the secret is, what the brain's trick is for solving the cocktail party problem. And what we came to the conclusion was there's really 2 tricks involved working together. So that essentially the brain is doing 2 things. By the cochlea is separating sound into different frequency bands and processing them independently. That's one of the tricks. And the other trick is it's all processing the sound over very short time intervals. And the point is that, excuse me, is that speech is very sparse. So humans aren't really interested in listening to sinusoids or listening to white gas and noise signals. Humans are interested in listening to speech. They're typically non-stationary and also fairly sparse in time frequency. So in a speech-on-speech context, you have somebody talking here and somebody talking there and somebody talking there. And about 40% of the time, even when somebody's so-called talking continuously, there are short gaps in their speech. So 100, 200 milliseconds where there's silence between words or between sentences. So even if you have, say, 5 people talking at once, well, really there's only 3 people on average talking at the exact, producing sound exactly at the same time. And secondly, our speech actually has different frequencies. It sounds like ah, or low frequencies. It sounds like or high frequencies. So if you actually plot out the time frequency space, we're actually only occupying a very small portion of that at any given time. And we believe that's a trick that the brain's using. Essentially, it says if I map to this time frequency space over short time frequency intervals, even if there's 5 people talking at once, there's probably only 1 or 2 people actually in a given time frequency band at the same time. And so then my 2 degrees of freedom that my beamformer, that is 1 to capture the target, 1 to cancel, is often enough to get a really significant gain in terms of canceling out interference. And so the key trick here is like build an algorithm that basically separates sound into different frequencies and works independently with frequency, and does that very quickly, so it can quickly say cancel you here, and it kind of swap back and forth, and so move around quick enough to track the time varying nature of the speech and interference. I can actually get significant gain over with only 2 microphones. Again, this is the 2 element beamformer. We believe that's how it works. We built a fairly conventional beamformer that works the same way. We transform the frequency using the sound into different frequency bands using FFT, so kind of a crude imitation of the cochlea. And each frequency we kind of analyze the short time structure of the speech, the correlation matrix. We perform a beamforming there to keep preserve the target, cancel out the interference. We make it adapt very quickly, so it adapts over a period of about 100 milliseconds. And we just add up the remaining signals, cancel out the interferes, and put it all back together, and that produces an output. And if you do that, it turns out this is the performance that you can get. So when we have only one interfere, it still works just about as well as all the other beamformers. And so this black line is the frequency domain invariance algorithm we developed. So it's about the same as any other algorithm. It's a good algorithm with one interfere. But the nice thing about it, the very gratifying thing about it, is even when you have two or more interferes, when the standard algorithms break down and start to lose performance, this stays up there. It drops a little bit, but it stays up there pretty well. So it really gets almost twice as much gain in dB as so somehow this technique is somehow capturing, at least in spirit, the capability of the ear to deal with more sources than sensors. What's kind of intriguing is actually it's a fairly conventional algorithm. It's still just a standard FFT-based frequency domain beamformer. But of all the hundreds of possible implementations that we could have used of this, the biology was helpful to us to kind of realize that, hey, there's many hundred ways you could build such a beamformer, but this particular way, we're dealing with speech-on-speech interference, is going to perform much better than the conventional ways that we typically do things. Getting that insight was really a breakthrough for us. So here's just an example. Again, if you start working with biologists, they also get you to work on their problems too, and they can help them. And so actually I got involved in another project with some of my colleagues from that project to separate we call it frogs and chorus. So here we actually had a microphone array over a pond. There's actually hundreds of frogs calling around the pond, and this would be a mixture of the signal in one microphone. Seated by applying this beamformer, we were actually able to separate the sound into, in this case, pull out 4 separate frogs. Here you can see the strongest frog, we can see we're mostly going to be interference. But even the weaker signals that are much smaller than the dominant signals, we can actually see we can recover them and cancel out a lot of the interference. So we can actually do not perfect separation, but we can't get perfect separation with fewer sensors and sources. We can get a lot of SNR gains by using these biologically inspired algorithms. And so the current approach we're using is it's also known in biology that the brain does more than just beamform. It also has some ability because of what's called inhibition, so that neurons that are actually responding actively suppress the action of nearby neurons, and so they kind of suppress the performance of sounds coming from, say, other directions. And so we've actually recently been experimenting with techniques that try to do that as well. So in principle, it's known that we can build an optimal multi-channel arena filter by taking the output of the beamformer and then just essentially multiplying it by some kind of post-beamforming weight. But the challenge is we don't know what the various SNRs are at any given time in this signal string, so we don't really know exactly what we don't have the information to know what this is. So we've been using some ideas based on inhibition to try to build practical schemes that can actually strategically try to separate, reduce sounds that don't come from the right direction. And we're actually able to get significant SNR gain over and above what we get with the beamformer that you mentioned. Maybe I can just play a sound example here for you. And so this is actually recorded in a coffee shop. So there was music playing in the background. There was coffee grinders running and stuff like that. Let's see if I can get this to work. I'm not sure if I have enough. So I can turn that up here. What you get if you use a Microsoft Connect. It's a 4-microphone linear array. It's about 20 centimeters across.
Noise reduction systems conducted in a real cafe environment.
I guess significant cancellation, but it's still, there's some music coming through. And here's what we can get with
Noise reduction systems conducted in a real cafe environment.
Get a certain amount of distortion because we're actually canceling some of the targets as well. The bands that are dominated by interference, but you can hear we can get a lot of background noise suppression. So again, we think this is kind of a way forward to help try to get even better performance than the conventional techniques. Okay, so that's one kind of direction that kept keeping me active for a number of years in audio processing. But another question which came up, when I first started, my topic of interest was hearing aids, and so we were by binaural hearing aids. We'd have 2 hearing aids, a microphone at each ear, and they would exchange signals between the microphones and then do beamforming and processing. But then I got interested in the question of what if I wanted to try to get this kind of gain on a cell phone or some very small mobile device? Well, the problem is I don't really want to have a 15 centimeter long cell phone with microphones on each end or a Connect size array. I really like it to be smaller. So how can I get a microphone array that's small enough that I can actually put it on a cell phone or a camcorder or something and still get really significant gain? And the problem is that the way that beamformers conventionally work is that what we're essentially using when I have two microphones or more microphones, I'm essentially using a relative time delay between the microphones to tell the good stuff and the bad stuff. So basically, if I have two microphones like this, and you're straight ahead of me, then the sound arrives at both microphones at the same time. And the way I tell the sound coming from you is what I don't want to hear is that it reaches this microphone before it reaches this microphone. So we use that relative time delay or the phase difference in the frequency domain to separate the stuff we want to keep from the stuff we want to get rid of. But the problem is as I bring those microphones closer and closer together, then their relative time delay gets less and less. I have less ability to discriminate between the sound coming from this direction and the sound coming from that direction. And of course, I put the microphones right next to each other, then I totally lose my ability to beamform. I have no ability to discriminate the sound between one direction and another. So I can't do anything. So you think, well, so again, I was perfectly content with that as an answer that, sorry, you have to have aperture if you want to get a good beamformer to work, until my biologist friends introduced me to this guy. Has anyone seen the movie Alien? It's like a really old movie. It's kind of this old sci-fi horror movie. Well, basically, they got the idea for that from flies like this. So it's kind of gross. The way this fly's life cycle works is it basically hatches out of the body of a cricket, which of course dies, and then it flies around and finds a new cricket. It lands on that cricket. It lays an egg on the back of the cricket. The egg burrows into the body of the cricket. It eats away the non-essential organs first. Eventually, about the time the cricket dies, it matures and hatches and it flies off and finds another cricket. So again, it's really horrific. But that's its life cycle. So anyway, kind of gross, but the nonetheless, you can understand that for this fly to be successful, it has to essentially be able to find a cricket, right, and do that really well. And so the biologists have known about this particular parasitoid fly species for a number of years, but they didn't really, until relatively recently, know how it actually found the crickets. They were thinking maybe it can smell them or something like that. But then recently, a biologist named Ron Hoy at Cornell discovered that actually the way the fly finds its cricket prey is by, if it has ears, it actually listens to it and localizes the cricket. So this is kind of a blow up of the head. This is the head of the fly. It turns out that right here behind the fly is the ear, and the biologists are happy to tear off the heads of these flies. And if you tear off the head of the fly and look at it, you find essentially it has this ear right behind the head. And essentially it's kind of a very interesting structure. It has two hard plates, types, so kind of like just like this, the same material that the body of the cricket is made of. And it's like a weird kind of crossbar that couples these tears at the top. That's kind of marked up there. And so the way this fly's ear works is as they tell me, is that essentially when a sound kind of hits this ear, there's really kind of two modes are excited in this somewhat rigid structure. So there's kind of a common oscillation mode where essentially both ears kind of flex like this. We call it kind of an omni or a common mode oscillation. There's also kind of a rocking motion where the sound kind of will hit this side first, kind of tilts and rocks back and forth like a teeter-totter. And it turns out that this crossbar here has the mechanical coupling, which is just very carefully sort of balanced so that essentially on the far side, the common mode and the differential mode cancel each other out. So essentially if the sound's coming from the left side, this side oscillates like crazy, and this side hardly ever moves. The sound coming from this direction, this side oscillates like crazy, and this other side doesn't move. And there's kind of a really unique neural amplifier, which is effectively a time delay neural amplifier that increases that response, in terms of response to the time delay, and the brain can somehow then sort of figure out which direction for the fly to turn. And you can actually probably, if you look on YouTube, there's some really kind of fascinating videos of these flies in action that I've seen. And it turns out that they've shown with some really clever experiments, these flies can actually locate the cricket prey within about 2-degree accuracy with this ear, which is between 1 and 2 millimeters across, or about 1/40th of a wavelength aperture, so way, way, way below the rate of emission. So kind of an incredible technology if you think about it. And again, something that you would never have thought until we learned about these flies, that it's actually possible to get that kind of accuracy with such a small array, small ear. So now that we know kind of how the fly does it, the question is, well, what can we as engineers do? Well, so one possibility is we can say, well, use the idea that essentially what the flies that are using is they're essentially converting the direction of the sound into relative intensity differences, so that the relative levels of strength on the two microphones, in this case the ears. And so the question is, can we build a microphone array that does the same thing? And the answer is we can, and now that we know that the secret. we can actually do a combinations of directional and omni microphones. So omni microphones have kind of a common response to the sound. It's the same, you pass the sound with the same gain, regardless of the direction of the sound. But you can also buy directional microphones that essentially will have a kind of a figure-8 type pattern. So if the sound's coming from here in this direction, you get 0 response. If the sound's coming from the 90 degrees, you get a really strong response, and 0 on this microphone. So you can build microphones that have different directional patterns. And so what happens then is that the sound from different directions has different relative strengths on the different microphones. And the wonderful thing about this is directionality is built into the microphones. So I can put these microphones right on top of each other, and it still works. Because there's still the strength, the difference between the sounds is not based on the separation between the microphones, which is based directly on the direction of the sound and the intrinsic response of the microphone. So we can build these acoustic vector sensor arrays. Here's a couple of arrays that we built according to these principles. And here is one that's, and again, these microphones are about 4 millimeters across. This array is about the size of the tip of my finger here. And here's kind of a mock-up hearing aid that we built, which is kind of like a behind the ear area with a lot of different microphone combinations we were using to experiment, see if we could get really good directional performance on a single hearing aid with such a system. So we can actually build very small arrays and work with this. And it actually turns out that that can work pretty well. And the question is, well, then what kind of signal processing do we do behind that? It turns out, just by good fortune, that the beamformer I mentioned before, that frequency domain invariant beamformer, we almost always use these beamformers on arrays of omnidirectional microphones that are separated in space. But it turns out the mathematics doesn't care really whether the microphones, the difference between their signals are due to phase delays associated with time delays or relative strength. So it turns out the math works for relative intensity differences as well. So we can actually potentially take the exact same algorithm, put it on to these microphones, and it'll also give us a nice directional beamformer. So in effect, in some sense, we've done something that biology can't do usually. We put a mammalian brain behind the fly's ear and actually built this kind of a hybrid timer system that actually works remarkably well with a very, very small aperture. And if you can do this with many different combinations of directional and omni microphones. Gradient microphones combinations tend to work best because the responses are most orthogonal, but again, you can use other combinations as well. So let me show you kind of how that turns out. Doing the exact same experiments I showed you before. We're just going to combine all the different average of different performance of the different configurations. This is 1 interfere, all the different cases with 2 interferes, 3 interferes, and 4 interferes. The dark bars are what we saw before on the previous chart is the summary of that information. So again, you get substantial gain with 2 microphones 15 centimeters apart. But here with 3 microphones, an XY omni microphone, we do even better. So again, and the data right now is again less than a centimeter across. So we can actually get remarkably good beamforming performance and they'll just separate sources and cancel out interference with a tiny array we could put on any kind of mobile device. So again, that's very exciting to me because it makes it possible to get to take these techniques down to a size where we could actually do some really interesting things with them. And so another question that comes up in some of our multimedia applications is, well, maybe it sounds better to me, but does it actually work better if I feed it to a speech recognizer? Because if I want to use Siri or something like that on my cell phone, is it going to really help improve the performance there? And the answer is yes. Here's just a whole bunch of different sound sources put into a system without, for instance, using the omnidirectional microphone. And here's using the output of the beamformer. And we typically see kind of the 10 to 15 dB SNR gain in terms of, or in other words, the speech recognizer will achieve a certain level of performance with 10 to 15 dB lower SNR if we process the signal with this beamformer. So again, that's kind of exciting too. So it means that these results are actually useful for ASR type applications as well as for just human speech communications. Okay, so that's what some of the advantages or gains that we've gotten from trying to do in terms of source recovery, recovering some source of noisy environments or in speech-on-speech type situations. Let me talk now a little bit and change gears and talk a little bit about actually locating the source. So what's the direction? I think in some I'm kind of intrigued by this because I believe in some multimedia applications, if we can actually combine basically the locating the source with audio and also use the video together, I think we can do some really interesting applications. So for example, we can maybe steer cameras if we can sort of have omni sensing, just like we do. If somebody shouted my name behind me, I would turn and look at them. So we can use that for some of our multimedia applications. I actually also like the effect if I'm recording with a video camera, if somebody walks off the side out of my view, it's really nice to be able to hear them coming from that side. And so again, I think we can do some really interesting things by combining audio and video source localization together. But we again do put this on a small enough platform that we can actually do this with small devices. So again, here we're using human hearing as our biological inspiration. And so as I already mentioned before, two of the tricks that here uses is it separates the sound into different frequencies and locates sound sources independently, separately into different frequencies. It also does this over short time intervals, so if there's just kind of a short burst of a sound in a particular time interval, we can just locate that, and then at other times in the sound we can remember where it was for later. And so those are two of the tricks that here uses, probably the most important ones. But it turns out that the deer has two other tricks that it uses as well, which I'm going to mention to you now. First of all, we're actually very good at dealing with background noise. So probably if I'm just quiet for a minute, try to listen, you probably can't even hear the hum from the audio system. If you think about it, you can hear the AC noise in that hum, but you're normally not. Your brain normally just kind of tunes out any steady background noise, just kind of ignores it, tracks it, and ignores it. So you can actually sort of track and cancel out background noise and then just listen for sounds that kind of rise above that noise. So that's one of the tricks that our brain uses. And the biologists have some understanding of the neural circuitry that does that actually. Another thing we use, which is kind of even more remarkable, is something called the precedence effect. And essentially, this is a problem in a real world like this. I have a lot of echo in this room. If you actually just apply the standard beamforming algorithm to try to figure out where the sound's coming from, they very often break down because it turns out that you have all these echoes coming from this direction and that direction, and it's really hard to kind of figure out exactly where the sound is. Well, the brain has a trick for dealing with that, which the psychologists know the precedence effect, and essentially it works this way. One thing about the sound is if you have a sound coming from some particular direction, the sound that comes directly from the sound source to your ear gets there first because it's the shortest path. If you have echoes, well, they may bounce off a wall or something that can come in later, but they take later to get there. So in some sense, in this particular case, the blue bars might represent a sound that arrived that was coming directly, and the green bars might represent these echoes. In this case, you'll notice that the echoes arrive at different times and different years because it's a longer path. The echo changes this year than this year. This is what actually the sound that arrives at the ear. But what you actually hear is the brain has these circuits that essentially, if you hear an onset of sound, here's this big sound kick in, it essentially turns off the hearing for about 50 milliseconds after that, and you basically don't even hear, you can't even hear the sounds that come in later. It's kind of automatic circuit, very low level in the brain, but essentially gates out sounds that come in after an onset. And so we've actually included this in our algorithm as well, and it actually really improves our performance to dealing with, to locating sounds in reverberant environments. We have a lot of echoes in any kind of indoor situation. So the overall, the technique we use, it works a lot like the thing I mentioned before. We separate the sound in different frequencies by short time Fourier transforms. We kind of track the signal over each time domain at each interval. We essentially look for intervals in which there's only one sound, one dominant sound. We locate sounds in those intervals, otherwise we say we can't do anything. But we also test for onsets, and we also track the noise for and cancel out some of the background noise. If we combine all these things together in one overall test, it turns out that we can actually locate sounds to very high accuracy, and we can also collect in more sound sources than noise in kind of a typical cocktail environment. So I can just show you a quick example of results. Here's a situation where I had 3 microphones, each an inch apart, in kind of a little L-shaped configuration, and 7 acoustic sources, so 7 people talking around at once. Got a meter from the right. You can see actually that if we kind of do a little instantaneous look, in each of these is basically where the sound source appears to be at each time and frequency in the data. You can see we get clusters around different time intervals. In this case, we can see the 7 clusters which correspond to the location of the 7 sources. And if I fuse all these data together, I can basically get kind of a map that shows me, in fact, I can actually see that I have 7 sources in 7 different directions. These are accurate within about 2 or 3 degrees, actually, even though they're all talking at the same time. So again, this algorithm, again, it gives us some hope that we've actually somehow figured out one of the tricks that biology uses to be able to solve this problem of localizing more sources and sensors in a reverberant, noisy background. And we've also applied this outdoors as well. So this is a case where we're tracking a tank driving around in the field. And again, we use that acoustic vector sensor array, the XYZ on the array, and we can actually track that to 2 to 3 degree accuracy as it's driving around just by using the same type of algorithm. So again, we can localize these sounds, and the key thing is that we can do it fairly well. We can do it, and we can do it with a very small array. Okay, now another thing that's always intrigued me, as I said, I really like, to me, I prefer 3D audio to 3D video. So if you give me a choice, I'd like to have kind of a 3D spatial experience. And so one thing I've always really wanted to do is say, can I somehow get the ability to record with a very small, with my cell phone or say some camcorder? Can a consumer device, can we record and get kind of the whole 3D audio experience? But I've always thought I would much prefer home videos and stuff if I could actually record and kind of preserve that 3D audio ambience. So that's been an interest of mine for a while. And so the question is, well, how do we know how biology actually does directional sound? Essentially what happens is the way our brain can tell what direction the sound's coming from is sound coming from a different direction. It arises at this ear before it arises in that ear, or arises at this one before that one, depending on the direction. And also there's some head shouting effects, so if the sound is coming from this direction, it's blocked a little bit by my head, so that it's a little softer on this side and this side. So since it is this so-called head-related transfer functions, the relative strengths and time delays of the signal at different frequencies, our brain somehow fuses all that information to identify the directions the sources are coming from. And so we can essentially say that the source that we receive at any given ear that actually is going into my eardrum is essentially a sum of the source at a particular angle theta, it's a combination of all the sources of theta, plus the corresponding head-related transfer function that reaches that ear and the right ear respectively. I can kind of write that in the matrix form as I have my vector of sources with different frequencies. This left signal is the combination of the different HRTFs to the left ear, and different sources, and the same for the right ear, of course, correspondingly. And so that's what I should hear, right? Now, if I've actually recorded the signal not with my head, or not without microphone, but I recorded it with the microphone array, the directional array I talked about, I actually get kind of a similar, I get, like, say, the microphone-related response. So, for example, in this case, I have an array of 4 microphones, and I have my sources from different directions. Well, essentially, there's these kind of specific filters or corresponding to each direction, which might correspond to, say, the relative gains and the time delays to each of those directions, which gives me an overall response to each microphone. So what I'd really like to do is I like to put this acoustic vector sense array on my small device and record with that. And later on, I'd like to map that sound from basically, if you will, the microphone-related response to the head-related transfer response. So essentially what I do is I'd like to take that signal, run it through some kind of reconstruction filter, reconstruction processing, and reproduce a sound that was as close to what I should have heard in the real world from just the actual response through the head-related transfer function. And actually, once we kind of realize that's what we want to do, we can actually just set this up as a least squares problem and solve it, and basically essentially find the reconstruction filters that will produce the most accurate reconstruction in least square sense to what I should have heard if I was actually listening through my own ears instead of through the microphone array. And if we do that, we actually can produce pretty good results. It's not as good as recording at the ears, but it's a heck of a lot better than monaural. And I can't really play an example because you really have to have headphones on and hear both ears at the same time to hear it, but I'll be happy to those who are interested. Anyway, you can do this, and it gives us, again, it's not as good as recording at your ears, but it's definitely a much better effect. And the nice thing is I can do this with that small array and do that on any kind of mobile device, no matter how small it is. Now, it turns out that, and the nice thing is you only need 4 channels to kind of get this universal response. It turns out this has already been thought of by engineers. So in this case, even though biology thought of it a long time ago, engineers thought of it without it. It's called ambisonic speed format recording. But you actually can use this reconstruction technique I talked about before to do this with different types of arrays as well. So as long as you have a combination of arrays, microphones in different places on your mobile device, you can actually reconstruct your get a decent kind of response. So again, this is kind of exciting to me because I really would like to have kind of 3D audio recorded with very small consumer devices. Okay, let me change gears here and spend just a couple of minutes telling you about another class of problems that I've been interested in. And if I want to put these kind of really neat audio features and pretty sophisticated audio features on a small device like a mobile phone or something, well, the problem is I really also want the battery to last for a long time. So the problem with a small device is that the array is small. If I have to have a big battery to power that array, then it's not really helpful. It's not really small anymore. So as we go and get techniques that work for very small arrays, also need techniques that are very power efficient and energy efficient, because otherwise I need too big a battery. So the question is, how do we build audio systems that are actually very, very low power, that if low enough power, like run them for hours on small devices with very small batteries? And in this case, I've actually been guided by biological inspiration and animal behavior to come up with some techniques that can reduce the power consumption greatly with mobile multimedia devices. And so essentially, I'm over-exaggerating a little bit here, but if you ask how do engineers typically design systems, we're always trying to do the best we can. We want to have optimal systems, so we're always essentially going for the kind of the full front. We're saying, I'm going to design a new algorithm to be the best algorithm that's ever existed, better than anybody else in the literature, and I'm going to achieve the best possible performance. And, how much does it take an hour? How much processing it take? Well, it takes a lot of processing, but still it's better than the other algorithms. And Moore's law, after all, is going to catch up in 5 or 10 years, so it's going to be cheap, and we can do it. So that's kind of at least how I typically approach my research. And again, I think that's sort of engineer's attitude. Let's build the best possible system, the highest performance. And we only kind of worry about energy after the fact. We say, that's pretty expensive. And then you sort of maybe start cutting it back until you reach your energy, you can achieve your energy budget and say, okay, well, good enough. I'll stop there. So that's how we typically design systems. Energy is kind of an afterthought. But let's talk about how nature designs systems. The way nature really designs systems is we don't work that way. So cheetahs, the world's highest performance land mammal, right? They can run faster than any other animal that exists. But if you think about it, because how often do cheetahs run at full speed? It turns out cheetahs only run at full speed like about 1 minute a day. So in fact, if you like me and you like to watch the nature shows on PBS, it turns out that essentially cheetahs can only sprint at this full speed for about 30 seconds. After they have to rest for about 15 minutes before they can actually run again. In fact, it's common they often get their prey stolen from them by other animals because they're so exhausted after catching the gazelle that the hyena or something can come in and take it away from them and they can't fight back. So again, even though the animals have a pretty high performance, they only have that high performance at very short intervals of time. And why? Well, the answer is because most animals starve to death. And if the cheetahs just running around at 70 miles per hour all day and all night, it wouldn't live very long. It would run out of energy, it would starve. So the way animals really work is most of the time they're kind of sitting around sleeping. Cheetahs sleep, I think, 20 hours a day or something like that. And then for the rest of the time they're kind of walking around looking for possible prey. And they only try to run at full speed. They only expend a massive amounts of energy at this exact times when there's actually a high probability of actually getting some benefit from that. So again, they're scalable systems. They adjust their energy consumption to the environment, the current situation. And they mostly operate at a low performance mode, and they only operate at high performance mode when there's really no benefit to doing so. And again, it's a little bit different than the way we typically design systems. Usually as engineering systems, we kind of design for high performance or off. We turn a thing off and turn on. So we kind of have two modes, full performance or nothing. Animals kind of have a gradated performance. They can kind of adjust through the domain. And so we were interested in asking, how can we build systems that are scalable where the algorithms and the performance is kind of gracefully adjustable from relatively low performance, but still useful performance and low energy, up through really high performance and high energy, and how can we intelligently decide which operating point you're working at any given time. And so there's many strategies you can use to design scalable systems. And so one is you can try to essentially screen out information. So if you're kind of sleeping at night, your ears are still working, not very well. But if you heard of some really siren or something really loud noise going on, you wake up and think, what's going on here? So our system is still kind of listening at kind of a low performance level, but it has this kind of wake up ability, so ability to learn to scale up to higher performance. Another thing we can do is we can trade off communications versus computation. So for example, if I have a device on a mobile device, I can say sometimes offload computation to the cloud, for example, and do some stuff locally. I can make an adjustment depending on the relative energy cost of moving data as opposed to the computing locally. We can also exploit the time-varying environment. So what animals are remarkable at, the animals are always adjusting their energy consumption and their performance on the basis of kind of what's happening around the world. It's a dangerous situation, pay a lot of attention. If a predator's chasing you, run quickly. If nothing's happening, save energy. And so we can also, I think, build intelligent systems that also make that kind of dynamic adjustments to the environment. We can sense the environment well enough to make intelligent decisions. And the other thing, again, about animals is we're always making a decision how much energy to expend on the basis of how much I expect to gain. So that cheetah only spends all that energy chasing down its prey, but thinks it's got a very good chance of catching that prey. And it's going to spend longer energy chasing after a big gazelle than it is after a little mouse or something. So again, we have this ability of adjusting the energy input relative to the expected gain, or essentially we maximize the utility of the performance. I think these are ideas that we can use to try to help design systems that perform well. Now, in some sense, this kind of concepts are really not new, so engineers have tried this in the past, so you'll be aware of some of this work, I think. There's been work in cascaded detectors. You have kind of a low-performance system and high-performance detectors. So, for example, in voice activity detection and speech, typically the speech recognizer only runs if you detect that there's voice. You have kind of a low-cost algorithm saying, listening to the sound, and only if you hear the sound like speech, do you actually feed it to the Siri system or the voice detector. There's a technique for simple internal refinement, and many of you may be familiar with the Jones algorithm for face detection. And again, it's kind of a cascade system. It has a lot of low-level processing, and then only basically does the more sophisticated processing on the regions of the image that look like they might actually be faces. So these are all kind of good engineering kind of ad hoc approaches for dealing with that. And it turns out, though, that you can actually put a more mathematical framework behind this and really actually optimize the energy consumption. So what we've been doing is kind of taking this one step further and saying, let's define a notion of utility. So what's my payoff, and what's the energy cost for every action? And we essentially say optimize the operating point relative to that. And so again, we can actually set up different types of systems. We can set up these optimization equations, actually find the optimal operating point, exactly how should I balance between the two systems. And if you do that, you can get pretty good performance. So here's an example where we were had a detector here and looking in this case for narrowband signals, acoustic signals and noise. And this is what would happen if you just ran the optimal algorithm all the time. You take this much energy, the performance would be almost perfect. But it turns out you can scale the energy down by almost a factor of 10. You can sort of slowly even get relatively good performance. Eventually, of course, you start really dropping your performance off. But this optimized scheme works a lot better than these kind of ad hoc schemes that just sort of have some good intuition behind them, but don't actually have an number to optimize the system per se. And we've actually built a system that works like this, just to kind of test this out. So here's a system with a low-power microprocessor, a little microphone that my students built. And we've been found, just to kind of give you a scale, we can get about 24x energy savings. So we can really cut the energy cost by about a factor of 20 with a system like this, with almost no loss of performance in this situation. In this case, it was a wildlife monitoring situation to listen for birds of different species. And with that's what announcers say to suggest you can even get even better gains. So I think this kind of strategy, although again fairly simple, can actually lead to performance gains, say 10 to 100x orders of magnitude energy savings without a whole lot of sacrifice in performance. And again, I think this is kind of what you see with animals. They can do, they're capable of really strong performances sometimes, but they're very selective about when they actually use all that energy. So again, I think these are strategies that we are seeing in the multimedia space, but I think we can do a lot more of that, and we can do that better. So with that, I'll just maybe kind of close with a couple of final thoughts. So as I mentioned to you, I've been working now, I think it's been about since 1997, so 17 years off and on, I've been interacting with biologists to try to help understand how we can use some insights from biology to help design engineering systems. And again, what we I conclude is that nature's already found some pretty good solutions to many hard problems, particularly some problems that somehow we find easy to do, but as engineers it's been difficult. And so they're not necessarily the best solutions out there. There's no proof of optimality of these systems, but still at least they're good solutions. And so in situations where our best engineering efforts kind of run up against a wall and we're not really being able to move forward, sometimes biology can give us helpful hints. The challenge with it is that usually the brain is extremely complicated, and the biologist can't give you like the whole system. They can't give you an entire block diagram. This is exactly how it works here, just build this. Usually you get parts that you say, well, it sort of does this, and it does this, and we have no idea what it's doing over here. So they give you kind of partial information, kind of hints, but not full answers. And so again, that's kind of the hard part, but also sort of the fun part is to kind of see how you can use some of these hints to maybe figure out how to do better. In my own personal opinion, I think inspiration, not imitation, is really the best way to go. So, it turns out biology gives us good ideas, but biology has its own constraints. So, for example, it's working with neurons, which are very small and very slow. And we're actually working on electronic systems. There's a difference between a neuron which runs at, say, kilohertz and a microprocessor that runs at gigahertz. You might not want to use the exact same algorithm for, say, transistor-based technologies for neurons. So we don't necessarily want to blindly copy exactly what neurons are doing. My belief is what we really want to do is try to understand the why. Instead of what's this system trying to, why does this biological system work the way it does? And then feel free to say, well, okay, now that I understand why it's doing what it's doing, what the trick is, maybe I'll build that in a very different way. But at least I give the inspiration as to kind of what the secret is to build something in a different way than I would have otherwise. And so that's when we had the most success by, again, kind of using rather loose inspiration, not just kind of blind imitation what the biology is doing. And in terms of kind of where I think, there's places, speaking for myself, I'm really now interested in, again, problems that I don't know the answers to. So essentially, particularly I'm interested in multimodal processing, so kind of combining video and audio together, multiple senses, seeing how we can do that. Animals, we as biologists, as humans, we use our eyes and ears together. You wouldn't want to have a blind security guard out there, or a deaf security guard monitoring your complex or your airport or whatever. So we use senses together. We combine these senses together. So how to do that, though, is, I think, a complicated problem. And I'm not smart enough to figure it out on my own, so I'm dealing with biology for hints on how to do that. And the other thing that really kind of gets to me is that the robustness issue. So, I can't tell you how many times I have built an algorithm. I thought, this is a great algorithm. I run a simulation in MATLAB. It's like, oh, yeah, it works great. I go report in the anechoic chamber, and it still works great. I go out and put it in a real room, and it's like it breaks down completely. It's terrible. And again, I get very frustrated with my algorithms that break when I get real-world signals in real-world environments. So I think getting robust algorithms that work in a very complex environment is really important for us. And again, I just can't seem to figure out this problem on my own as an engineer. So again, I've been turning more and more to biology to try to get some hints as to how to deal with those kind of problems. And I think that's also true of a lot of the techniques that we have as engineers. A lot of times, one of the big problems we face is algorithms not working in different lighting conditions and different environments. So if we can figure out how to build systems that are more robust, I think this is going to be a key step forward in building systems that are more widely applicable. So anyway, that's kind of where I'm looking for inspiration. And again, I think because I'm not very smart, I guess, so one thing I biology can help me give me some clues on how to do this. With that said, thank you very much, and I appreciate your attention.
So going all the way back to cocktail party and how humans do it, that kind of thing. To what extent, if you know, does semantics come into play? In other words, as an English speaker, am I just as able to do this with a language I don't know, or does it matter that I can anticipate, the conversation? I'm starting to hear it, and then I know what the next word is going to kind of be, so I'm anticipating that.
Yeah.
So, do those higher level semantics come into play at all?
That's a really good question. So again, as always, a biologist have partial answers to that, so not complete answers. The answer is that yes, it comes into play to some extent, but not as much as I would have thought actually. So in some contexts it does, and there's additional gain above the the gains that I kind of showed here. That in some circumstances we can get by knowing that. There's also sometimes there can be actually performance losses as well. So for example, if you take a situation where you have, say, multiple speakers talking, and if the interferes in a language you don't know, actually you do better than if it's in a language you do know. Because actually sometimes your brain can get distracted by that other language and listen to the other person instead. Now for the target, the one you want to listen to, actually you do better if it's, if you get information. So again, it's kind of not, there's kind of good side and bad side to that, but it's apparently very complex. But if you're looking for literature, they typically, the psychologists call it informational masking. So that's if you want to kind of see a keyword to search for, there's actually kind of a fairly substantial and growing literature on those exactly those questions. But it appears that we actually do an awful lot, again, more than I ever expected. We do it at a very low level somehow. With the way that we still don't probably understand.
Do you collaborate with the sound producers like Dolby and stuff, because they claim to be able to place sounds in a movie theater at a given place. So they they use opposite technique to yours, but I think I don't know if you collaborate with them about that.
Yeah, I haven't much actually. I'd be interested to do so, but again, they have their own agenda and they're hard to get to. One of the challenges I think that comes up there is that so they're typically, because the money's there, they're typically interested in movies and sort of professional media. In that case, if you actually think about kind of the 3D soundscape, the sound in the movie is extremely artificial. So it's all recorded as mono recording. Actually, a lot of times the voice is actually recorded separately in the studio, voiced over, and then it's all mixed by sound engineers. So the kind of effects you get from a movie theater are actually really, there's a spatial effect that's actually very artificial. It's all designed by and crafted by the engineers. So in that sense, they're not really interested at all in 3D recording, because they actually want to create not the real sound, but even some super sound, right? They're trying to go for special effects. So in that sense, they're not particularly interested in the 3D recording aspect of things. They're interested more in kind of a playback through surround systems. I actually prefer to be more interested in kind of what can I do at the home with the sake of real world recording. It's actually of less interest to the media producers because they actually want to do more than that. They don't want it to sound like real sound. They want it to sound better than real, really. Get down to special effects.
From the sensor side of the house, I love the localization part, being able to find out where the things are. There's some work that people are doing with cane toad monitoring in Australia.
Sorry, with what?
Cane toad monitoring.
Oh, okay.
Invasive species, someone brought it in by accident, right? And so they're trying to figure out how many there are, what the number is, so they have to kind of figure out what the call is. So this stuff seems like it could be perfect for that. Question I had was, in terms of tracking, I think it's really useful to have, this kind of localization tracking. Can you explain a little bit about how much degradation you see as the, it seems like tracking would be a harder problem than, single isolated pitches.
Right.
And so how much of a degradation hit do you take when you have kind of a, thing that's moving?
Right. Yeah, great question. I don't have a good answer to that. So most of our work has been really focused on kind of the earliest stage processing, just kind of localizing over a very short interval of time. Just kind of getting back to your question, I mean, our brain does more at a higher level in terms of kind of using prior information and where the text was to follow it. I myself, we haven't really taken that next step to try to exploit that. And secondly, I think that, the greater challenge is in some sense the biologists, essentially the closer you are to the ear, to the sensory neurons, the more they know. And if you kind of get higher and higher level, they have less and less understanding of how the brain works. So frankly, I think the acoustic scientists have relatively little understanding of how the brain fuses information over long time and tracks. So it's a really great problem, and I know there's a lot to be done there. It's just that there's less hints available from biological literature as to how to approach that problem.
Well, let me ask a sideways question.
Sure.
So how long a sample do you need to get the accuracy that you were showing? Because that might give us hints as to.
Right. Yeah, in fact, we're typically using about 100 milliseconds, 50 to 100 milliseconds.
That's pretty small.
Yeah. And and you can do that too, right? So if you hear a clap or a gunshot or something, you turn, you turn before the signal reaches the cortex actually. So in other words, it's very, very immediate. And of course, this makes sense, right? Otherwise, you wouldn't survive very long if you did this. So some of these responses are more or less semi-automated. They're actually fairly low-level responses. But then kind of this higher level, more, okay, well, while you're turning, your brain is still trying to figure out, what was it, and processing later. So it's kind of a very complex and sort of parallel system that's running a lot of things in parallel. So again, we have, again, to me as an engineer, we have our short-term immediate response capabilities are much more capable, much faster at lower levels than I ever would have thought before. In other words, we don't really use high-level semantics as much as I would, we don't depend on as much as I would have thought. I don't think we use kind of longer-term tracking as much. We can do a lot without that, but we certainly do better with it. It's just that the biologists have much less understanding of how that kind of fusion over time happens. Because you get every time, if you understand 70% of what this circuit's doing, and then 70% of what the next one is doing, by the time you accumulate 3 or 4 or 70%, what you really understand is going up here is you really have almost no clue as to what really is happening 3 or 4 layers in. And so they're working all the time and learning more, but still I think in terms of that kind of higher level processing, how we exploit semantic information, longer term temporal dynamics and things, my knowledge of all is still a long way from really understanding that.
Thanks for a very inspiring talk.
Thank you.
I think a lot of the biological systems are like feedback systems. They have some kind of feedback loops that are sensitive to environmental changes. So how important do you think are feedbacks being designed? There's another approach to simply just taking inspirations, right, and to design the system, which is still mostly designed by humans.
Right.
But when it operates, how important do you think are feedback loops or controls?
Honestly, I think that's the number one trick that we use. I think that's in fact probably the most important. Moving forward, that's the most important thing to add into it. So yeah, I should have mentioned that. I don't know how to do it yet. I'm really, I'm starting to work on it because I think that's the number one step forward. We do it in a lot of different ways. So, we don't just sort of sit there passively and listen. If we hear a sound, we turn our heads, we move, we go towards it. And that dynamic kind of motion in the space and active sensing is really key to improving our performance. I think so that's one aspect of it. But even in the ear, so for example, it's known that there's feedback from all levels of the brain, from the cortex all the way back down to the ear, all levels in between. It's actually controlling the instantaneous gain of the sensitivity of the ear to different frequencies. Its response to different types of sounds and stuff. So there's a massive amount of feedback happening at all levels in there. Unfortunately, that's just very poorly understood at this point. But it's my belief that that is the number one trick of the brain. It's all about feedback. And so, again, it's just really, really complicated because it makes the analysis, or it also makes the scientific experiments to try to piece apart the feed forward and the feedback on different levels to kind of isolate that. It's extremely hard in terms of the biological experiments. But yeah, I think that's the future. Absolutely. Thanks for bringing that up.
Any other question?
So I have one more on the experiment with the localizing the sound from the frogs in the pond.
Right.
How did you handle ground truth? Because you only heard all 4 frogs at the same time.
Right.
So how do you know that you actually separated it correctly?
Right. Yes, that's a good question. So it turns out that in a previous experiment I didn't show the results from, we actually went out with a flashlight and actually put a bunch of stakes in the ground in a 1 meter spacing and marked out the big grid, and we actually got a flashlight every 15 minutes and actually looked at it physically.
The front shut off like this.